So welcome everyone to the second seminar of our visitors this week. Today's talk is by Professor Agata Rózańska from Nicholas Copernicus Astronomical Center in Warsaw, and she will tell us about two-phase medium frozen into magnetic field.
Thank you very much, and I would like to thank you for inviting me here. And finally, I'm sorry that I had to move my stay here because of many other responsibilities, but finally I came, and I will be happy to talk about two-phase medium frozen into magnetic field. The work was done mainly with Dominik Gronkiewicz, my previous student, Pierre-Olivier Petrucci and Renaud Vermont, but now I have two new students. Raj is here and also Paul Pisfasz, and I hope we will continue this work in the future. So, I would tell you about two-phase medium in the context of accreting compact objects. This two-phase medium is mostly observed in X-rays, so I currently use many X-rays observatories, and I'm involved in building Athena, new mission which is supposed to be fly in 2037 now, but we started to be involved in building Athena in 2013. So many years I participating in many meetings according to Athena. Okay, I was recently invited on absolutely nice meeting in the Lawrence Center. The meeting was based on not giving talks. It was just a discussion and 5 days meeting, but the place was nice, and finally I found a beautiful wall when every famous physicist was signed. And I said, wow, it is really a nice place, and maybe we can work on overcoming disconnects in understanding of accreting black holes. But you know, the meeting was like playing games every day. So I was, no, I'm not gonna, that's not gonna work for me, because we were playing games like in kindergarten, right? But finally, at least many conclusions were taken from this meeting. And the main major conclusion is that many scientists are really put it in some connects, and it is really hard to go outside of the box. Okay? So let's start. I prepared really quite a wide introduction for you to see where we are. Accretion disks are really very common around black holes across masses. We can meet them in active galactic nuclei, where the black hole is supermassive galactic black hole binaries around the black holes of stellar mass, and ultraluminous X-ray sources. This class of sources is really quite new. They are met on the rings of galaxies, and the compact object is still not fully confirmed. So the first disconnection, what we deal in accretion disk around black hole masses, is what ULXs have in the center. Are they similar as galactic black holes and AGN or not? Because in few sources, the coherent pulsation from neutron star was observed. So we don't know if those ULXs are around stellar mass compact sources or around maybe medium mass black holes. Nevertheless, beside of this, accretion is only the way to heat gas in the disk. But to see this disk, the plasma has to be cooled by radiative processes. And what do we deal with radiative processes? Maybe it is too basic for you, but I would like to switch those thermal processes, the importance of radiative processes, and how do they deal with observations. So basic, important radiative cooling mechanism for accretion disk is simple thermal cooling. And it directly gives us the temperature of the gas when the disk is around supermassive black hole in AGN. So disk is only 10 to the 5 kelvins. It's not seen in X-rays at all. In UL-axis, if we assume, which is not confirmed, the black hole mass is 10 to the 2 or 4, so intermediate mass black hole, the disk temperature is relatively higher, but still not high. The hottest and smallest disks are met in galactic black hole binaries. But generally, geometrically thin and optically thick disk does not explain this hard X-ray emission observed in accreting black holes. So here you have the example of the broadband spectrum from AGN. When you see the disk may be here, so far, far away, outside X-rays. X-rays start around 0.1 kV. And we have huge, wide observation above up to 100 kV. So it is really quite 100 kV. It means it's 10 to the 8 kelvins, right? So disk is not possible to explain it. So what is the origin of hard X-ray radiation in accreting compact objects, right? So disk is only here. So what other radiative cooling mechanism may explain it, right? So in case of AGN, the hard radiation was shown in the previous slide, but here black hole binaries may be a better candidate to trace it because disk is seen as in X-rays, right? It's here. But anyway, all this radiation above 10 kV is not explained by simple disk. X-ray binaries are smaller, and additional thing, what do we observe in X-ray binaries? It's spectral state transition. So in one time, for instance, the Cygnus X1 is the most famous binary. In one time we see the disk domination above hard radiation. On the other time we see that hard radiation dominates over the disk. And even if galactic black holes are the bigger representative of accreting disk around black holes, we cannot observe it in a galactic, in AGN because the longer time scales. And even if we assume the mechanisms are the same, and there is a kind of hot region responsible for this radiation, we don't still know what causes spectral state transition in galactic black hole binaries. Other radiative cooling mechanism, which is most popular, is simple Bremsstrahlung. So electron changes his way around the proton or other ion, and X-ray is radiated. This is very nice representation of thermal radiation from hot and quite diluted plasma. Bremsstrahlung depends on temperature and density, so explaining and counting this radiation from observation may give you the temperature, but what is the density of this emitting region? We have to have independent measurement of the density to understand what's going on. Another radiative cooling mechanism which plays role is synchrotron light radiation, but we need, of course, magnetic field we know all of this, but now in AGN model, do we meet magnetic field? We know magnetic field is connected to the jet. So, looking on the unified model of AGN presented yesterday by Ms. Farage, when we see the disk, we may expect synchrotron radiation, and this is really true. So radio-loud AGN usually have following continuum energy distribution. So the disk emission is completely hidden due to broadband emission, usually featureless, completely featureless, and X-ray radiation is just continuum. Maybe this is synchrotron radiation, but what radiation goes around those magnetic field is still a disconnection. Featureless spectrum of radio-loud AGN does not allow us to trace the disk. So the only spectrum which allows us to trace the disk is of course thermal spectrum and eventually Compton scattering. But for Compton scattering, we know the process, of course, very well. Photons interact with electrons, and gas can join temperature from photons, or eventually we can have inverse Compton scattering when photons join energy from hot electrons. But for both processes, we need seed photons to be present, right? So we need a substantial radiation pressure in the area, in the region of the emission. And here, the problem with Comptonization, the main problem which is still here, there is the origin of seed photons. So explaining Comptonization needs to explaining the geometry of the accretion source, and of course simulations of multiple Compton scattering are still very time consuming, we know it, right? So radio quiet AGNs are the best to trace accreting compact objects, right? But they are complicated. We know there is accretion disk. Accretion disk only represents this part of spectrum. Then, because we see this emission, we associate this emission with the hot corona of the unknown origin. We don't know where it is situated. We have some constraints. It is compact from reverberation mapping, but still it looks different in different sources. In soft X-ray, very often we see absorption edges, right? So we associate them to the warm absorber presented somewhere on the way towards the observer. But the major disconnection here is what is the origin of geometry and hot corona in accreting compact objects. So X-rays gave additional knowledge to unified model of AGN. The first one, the presence of electron-like plasma in the form of corona responsible for hard radiation, and then the presence of ionized wind, which sometimes is seen in 50% of AGN or not. This is still the best example of ionized wind made by Chandra in 2000, on the beginning of the work of Chandra, when you see a lot of neuroabsorption lines for the long exposure time observation. It was really very long, and they made a trick co-adding spectra. But the disconnection number 8 is how the ionized winds are powered. Are they disk winds or how they are created? We still don't know it. Okay, so coming back to accretion disks around black hole across masses, we have those three kinds of objects. We observe them hardly in X-rays. We see similar behavior of them, starting from AGN, when we see this huge amount of X-ray radiation coming from corona, some retrocession radiation. We see similar things in galactic black hole binaries, and finally in ULXs as well. So maybe this is not a good example, but the disconnection number 9 is it the common picture of black holes accreting disks across the masses? And this is still something what we would like to work on, and this is a subject of my new grant, what I got a year ago. Basically we defined 5 X-ray fingerprints of accreting compact objects, which are really common in all of them across the masses. So double peak continuum emission. So this one which may come from the disk, and the other one which may come from other region, soft X-ray excess and 1 kV, iron K alpha emission line complex, warm absorber, and soft X-ray lag. About iron K alpha and soft X-ray lag, you had some seminar yesterday, and today I will concentrate in this picture on soft X-ray excess visible in X-rays. Because if you look on the broadband energy continuum from those accreting objects, very often you see the disk here, some hard radiation, and very often additional emitting component, which is connected with additional comptonization, is responsible for the explanation of soft excess emission around 1 kV. So the only disk does not explain this additional emission observed by X-ray satellites, and I would like to concentrate my seminar on this topic, where soft X-ray excess is formed. And how do we deal with this? How do we deal with accreting disk at all? So on the one side we make GR-MHD simulations with quite adopted radiation, but a kind of simplified, and here you have big group doing this, Deborah and other people, right? So you have simulations, you see the temperature, but the spectrum is computed after those simulations are done, and you have the distribution on radiative pressure, you do it, right? And this goes smoothly. But of course, computational zone is just up to 25 Rg. It depends on your computer time, on many, you can spend many times of setting the simulations and dealing with them. And in those simulations, you see some mixture of matter, but it is hard to look where the matter has any instabilities or it is hard to feed the data with the result of this, right? On the other side, people are doing radiative transfer detailed simulations, taking into account precise ionization of matter, precise comptonization, iron lines, and many other heavy elements in different ionization states. And this is another huge work to do. But if finally we go to feed the data, we use simplified models. We think, okay, there is a disk, there is a hot something on the top of the disk, and let's assume this something has constant density. So you don't need simulations for this, you don't need complicated radiative transfer, you have constant density and you produce emission and you feed. And this is what we would like to, right? A bunch of papers on it is still coming. And now it comes to the definition of two-phase medium, finally. Two-phase medium and thermal instability is when you have this hot corona, because you have to have somewhere X-ray source, you see it. So this X-ray source illuminates cooler material and produces heated atmosphere with a reflection, right? And now you can compute it under constant density, but you don't need for this any complicated, happily you don't need any complicated relation. You can just assume ionization parameter on the top, which is the ratio of illuminated radiation to your density of the gas, and either it's constant density or maybe you assume some other structure of matter. This parameter works, it is an input parameter, and whole radiation can be computed through the layer, and matter structure just adds the complications. So the most popular ionization parameter in use is this log psi, but to emphasize two-phase medium, we need to define big psi ionization parameter, which is the ratio of radiation pressure to the gas pressure. And it appeared, well, it's not appeared only here, but it appeared that if you go with such a computation through the accretion disk in radiative equilibrium, it appears that in one optical depth you have 3 solutions on energy budget. So it means your medium can be a mixture of higher temperature medium with lower temperature medium of 2 different temperatures and densities. And how this two-phase medium deals with magnetic simulations, right? In the early work by Cynthia Hess, it was also shown that this two-phase medium, this unstable zone, which is very nicely presented as in the graph of temperature versus dynamical ionization parameter, the parameter when you have the ratio of gas pressure to the radiation pressure to the gas pressure, and if this slope is negative, it means the matter is thermally unstable. It depends on the abundances of oxygen and iron abundance gives us the more heating by absorption of heavy ions, and a more oxygen gives us more heating here. So it really, the matter abundance affects this so-called stability curve. And now we know why this two-phase medium is caused. It really depends on the radiative processes across your layers. So imagine you have here a slab starting from the surface to inside, and you go with your radiative processes self-consistently deep into the slab. If we have very good photoionization code, we can really compute Bremsstrahlung heating, comptonization, photoionization, line heating, and we really can reconstruct this stability curve, showing that this jump in cooling, radiative cooling processes is responsible for this first unstable zone, and this second jump is responsible for the second unstable zone. And in those two zones, the gradient of your cooling function over temperature within the constant pressure is less than 0. Right? So, and it is obvious that this two-phase medium is seen when the matter is out of the constant density. So constant density approximation just does not show it. You have to have a matter structure, at least constant pressure, or hydrostatic equilibrium, or whatever, to see those two-phase mixtures. And we made some work to see this two-phase medium in the centers of galaxies. We can see that it can be present in our galactic center and around Sagittarius A star by computing photoionization calculation with publicly available cloudy code. We can reconstruct this stability curve and show that for some luminosity states of our galactic center, we can see what is the extinction of this parameter, so how far from the black hole it is. So we did this work together with people in Prague, and we were able first of all to define really those two-phase media. How big are those clouds when the cold phase is a mixture with hot phase, and we could really place it as a distance from the black hole. So here is the Sagittarius A star, and we are going farther away and can define where two-phase medium, how two-phase medium is extended, right? It depends on the density, of course. It depends on the density of this matter. The similar work as an example of two-phase medium we made for Centaurus A galaxy together with Abjit Borkar. Also, he had this kind of work is really nice because you really can directly compare them with high-resolution images of in this case Centaurus A nearby AGN galaxy, and you have these colors are X-rays, Chandra exposure, and the contours are ALMA data taken by Abjit Borkar, right? And if you put them together, you see that for some extent the cold material overlaps X-rays, so maybe we deal with two-phase medium. And we did some simulations by Cloudy, and we found exactly the position when CO emission seen by ALMA is explained. It's really as far as simulations show. So those radiative processes matter. And now I'm coming back to soft X-ray excess. We have this disk. We see this additional comptonization which produces soft excess. So how to explain this? How to go through this matter? And we made two assumptions. We extended the picture by assuming that the disk is magnetically supported. So it is heated by magnetorotational instability, and the prescription of this was taken from Begerman because this was vertical prescription. They are not through 3D simulation, they are only 1D simulations, one maybe and a half. We made accurate treatment of radiation with radiative transfer, but we didn't go with ionization here. We treated only Compton and free processes, and numerical structure and vertical structure was computed in the different distance from the black hole. So solving this algorithm, it was done by my student Dominik Gronkiewicz. He, in radiative transfer, what he did, he assumed emissivity, free, and Compton scattering. The disk was magnetically supported in the way that some magnetic heating goes to the gas, and this was fully in hydrostatic equilibrium. And the whole model is parameterized by 6 parameters: mass black hole, accretion rate, and the radius, how far you are, and 3 magnetic parameters. It was a big time taken from Dominik to play with magnetic parameters, but in generally we did it as a way to following the output from simulations. So at least it agrees with simulations, with people who are making GRMHD. And in case of galactic black hole binaries, when we solved this structure, we found thermal instability, classical thermal instability, when this gradient of radiation cooling over temperature is less than 0. We found it in the structure of the disk. So you see here vertical structure, and everywhere where it's pink, the gradient is less than 0. So it's thermally unstable. Right? So here it has thermally unstable region, here is thermally unstable. For other parameters, okay, it's fine, it may be stable, right? Then we made a progress, so we took this magnetically supported disk for AGN case, which was also time consuming, because there is a big difference between the disk, which is cold, to the corona. But finally we were managed to produce the hot corona above, the warm corona above accretion disk. Here different lines depend different magnetization. When M1 model is the strongest magnetically arrested disk, and dark violet is the weakest. And Ti is clearly visible if it is computed under constant gas pressure. So you see here this stability parameter goes below 0. And theoretical prediction of soft corona from this magnetically supported disk, we have computed so many models, and we were able to see how the average temperature of the corona base and the coronal optical depth, something what people observe, how it depends on accretion rate and the distance from the black hole. So for strong magnetization, the corona optical depth is 40, and temperature is around 1 keV. For weakest, maybe the optical depth is smaller, but still corona is quite optically thick. Because of this computational scheme, we can theoretically predict where this two-phase medium, so thermally unstable medium, is located in the vertical disk structure. So here is optical depth, vertical optical depth, and here is the distance from the black hole. So we can see by this pink how, by this pink zone, how what is the extent of thermally unstable regions in the strongest magnetized disk and in the weakest magnetized disk. The pink zones are thermally unstable regions, and the black solid line is the temperature minimum of the soft corona, and the red dotted line is the position of the photosphere. So everything happens above photosphere. Corona is generated, is hot, and is hot, and sometimes it is stronger, wider, and sometimes for this accretion rate, for this magnetization, sometimes it disappears, right? It's completely stable. And rows show different accretion rate. From the bottom is the highest to the top. No, from the bottom is the highest. Okay, and now the question arises, why? Is it really thermally unstable or unstable? What it causes for the matter, right? And I was asking Dominic, I think, like 2 years to make this figure, or maybe 1 year, I don't know. But finally I made it myself because he didn't like this representation of ionization parameter versus temperature. But when you draw it for such a corona, for such a warm corona, such a stratification, you see that here you have this diluted soft corona, very hot, 10 to the 8, 10 to the 9. Then you have, of course, negative slope of temperature versus ionization parameter. It can be thermally unstable. Then we are reaching the base of the corona, which is optically thick. This is representative of two models, M1, M2, and 3, where M1 is the strongest magnetization. And then suddenly it turns again. It's still negative, but let's say less negative. And what does it mean? We started to draw stability parameters, so the gradient of radiative processes over temperature, and here the continuous line is under constant gas pressure. But when I draw it under constant gas plus magnetic pressure, this gradient is never negative. It's never negative, so it means classical thermal instability is like a kind of, maybe from classical point of view unstable, but adding magnetic pressure, it keeps this instability as a frozen, right? So it can sustain. This is maybe why it is not seen, this kind of instability is not seen in any GR magnetohydrodynamic simulations. Because here, if you see the pressure components, magnetic pressure always dominates 2 orders of magnitude over the gas pressure, right? Magnetic and radiation pressure dominate. So gas pressure is minor. And those thick strips represent the extension of classically thermally unstable regions. So classically under constant pressure. So the two-phase medium maybe exists, but maybe in somehow magnetic pressure keeps this without any evolution, but we don't know, so we should probably do magnetohydrodynamic computations. But what we did here in the same paper, we computed our all models, we put it together with observations. So people who work with data, they feed this soft X-ray excess as a second Comptonized model, and they derive from feeding optical depth and temperature. So we don't have a lot of data, but we collected all of them existing up to date, and we put it to our models, and you see they are really following those instability strips, right? So soft corona really nicely matches with our model of the base corona on the top of magnetically supported disk. The important thing is here that, of course, computing the disk, we deal also with other instabilities like the radiative pressure instability. So, and the important thing is that observations do not follow radiatively the unstable disk due to radiation pressure, but they follow only those radiation pressure stable disks, but thermally unstable strips, right? And conclusions. Okay, I hope you are following still me. And conclusion is that soft corona may be formed in magnetically dominated, magnetically arrested disks. The temperature and optical depth agree with observations, and circles here are observations exactly put it to the models, and crosses temperature minimum from our model. The strips, solid strips, are Ti instability strips. Ti may create X-ray emitting phase in multi-phase medium, but I guess they are stabilized by magnetic field. Why it can stay stable? My answer right now is it is frozen into magnetic field. And this is something what I think is the main conclusion from our paper. And now what we can do next to solve this problem, because this is something, this connection. So to do is now to compute timescales from this process, taking into account magnetic field. We could really estimate how it evolves. And this is why I came here to talk about those timescales with you, Deborah. So thank you. If you have any questions, I will answer.